Okay, let's start the afternoon session with David Berman speaking about strings, branes, and Boltzmann.
Okay, so this is going to be a little bit of a different style talk because I've got to do a lot of overview of machine learning and a particular approach to machine learning, which I'm going to describe. So I should emphasize this is very much still work in progress. And it's just the beginnings of some ideas, but I thought I wanted to share it with you guys. So at this conference, I've got to introduce to you neural networks, and then I'll introduce a particular type of neural network called the restricted Boltzmann machine, and there's an N missing there. And then I'll describe information metrics, which is metrics on the, is how you form a metric on the space information. And then the Bayes approach to statistical inference and how that becomes related to a quantum field theory. And then I'll describe what's called the Markov chain Monte Carlo, which is how we do sampling. And then how we can put these sorts of things together and relate Boltzmann machines to maybe quantum gravity and maybe string theory and then maybe M theory. Distributed. Oh, dear me. Yeah, distributed. That'll be clearer later. So there's a long history of theoretical physicists providing techniques for machine learning and also a whole bunch of other ideas that we used. And it goes all the way back to Hastings and Metropolis, and before that, Stanislaw Ulam, who first came up with the Monte Carlo method of sampling. And this is a central part of how people actually now do machine learning processes through sampling data and so on. And then more recently, there's been a whole load of work relating the renormalization group to deep neural networks and unsupervised learning ideas. So what I'm going to try and do is bring together a host of ideas that string theorists will be familiar with through Boltzmann machines and statistical inference. Okay. So I should give some cites of what I consider to be key works in this area. So I was very interested by, there's a paper by Mehta and Schwab, which first made the observation linking the renormalization group to restricted Boltzmann machines. And then subsequently there was work, very interesting work by Koji Hashimoto and a group in San Diego, which related then restricted Boltzmann machines to holography in gravity. And then once you've got that, you ask yourself, where are the strings in the restricted Boltzmann machine? And is there a quantum theory of gravity associated to it? And hopefully that's where we're going to get to. So this is the references way back. So this is our VJ, as in Vijay Balasubramanian, who we know from other work in string theory. He had a very early paper in '96 on the relationship of partition functions in quantum field theory to Bayes' theorem. Jonathan Heckman had a series of works which we related sampling to signal models, and I'll review all of this. And then, as I said, this is work by Schwab and so on more recent works. Okay, so I've sort of said this. Let's get on. So I've got to review for you a neural net. So this is what will be a neural network architecture. We have some input layers, and these are what we will call the neurons, a set of hidden layers, which are labeled H here, and then each one of these lines connecting layers will have an associated weight, and I'll give some notation in a minute, which takes the input from, let's say, layer I, node 1, to the next layer, and then a particular node in the next layer. And then you iterate that process, going deeper and deeper, and then you have a set of output nodes, which is what you want to read. So what is it that you do? So in the network, we have these weights, which takes you from one node to the next, as indicated there. We put in a visible layer, which is like layer 0, And then in each one of these nodes, we have an activation function, which has to be a nonlinear function. And here I've got some examples. This is called the rectified linear unit. And it's basically off or on linearly in various ways. Or you can have something called the sigmoid, which is like this. It's off and then goes on, or than and functions like that. So you take the inputs from, for example, 2, we'll go into the inputs here. You add them up, and then the activation function will be on or off according to that activation function. Okay, so that's the traditional neural network architecture. And then for supervised learning, what you do is you have a labeled data set. If you like, think of a set of handwriting that you've got, and somebody's gone through and labeled all the 1s, labeled all the 2s, labeled all the 3s, and then you train the network by altering the weights so that the output layer maximally, in some sense, matches the labels of the input. Okay? So what you're doing, and this is the phrase that's used, is you are basically training all the weights which are along these edges of this network so that you have a good approximation whenever you put the input function in that you get the labels out. And that's supervised learning. And there are various theorems that have been proven that neural networks are what are called universal approximators, meaning that you can put in, that you'll basically have the capability to approximate almost any function. Okay. Now, how you actually do that learning process, and what we mean by maximally matches, is then quite a sort of subtle process, especially if the network is deep. You have basically a landscape of where you are trying to get to some minimum where you match the data with what the labels are, and then so you do a sort of gradient descent process, and then the thing that's quite subtle is that you have to do what's called backpropagation. So if you just had one layer, this would be linear regression. But because you've got a series of layers, you have to iteratively backpropagate, which is very expensive. But that's what people do. And the success of people like Google and DeepMind is to do that thing efficiently. And that's dirty algorithms, which I won't describe. Okay, so that's traditional supervised learning. But it's not very physical in the sense that you have to have a labeled data set. In physics, nobody labels our data sets. The world around us is just data, and it's not labeled in one way or another. We just have implicit data. So Jeff Hinton, who's really the guru of machine learning, came up with what are called Boltzmann machines, and this will be a restricted Boltzmann machine. I'll explain the difference. And this is for what's called unsupervised learning. So I'll explain that. So it's very much as before. We've got a visible layer, some hidden layers, but here we don't have an output layer anymore, and we won't have a labeled data set for which we're going to then say, we want to then take the data and then match it and say, this is the number 1. So what do we actually do? So normally we have a set of binary data in the visible layer, which we denote like this. These are our hidden layers. And then we introduce an energy function as follows, which is basically given like this. So these are our weights from before between each consecutive layer. And then we've got these things which are called biases, which allow you just to give some additional, a bias to a particular node. And so taking the visible layer as level 0, then we have this energy which depends on each node, and then the weights, which are the interactions in between. And then what you do is you take this Hamiltonian, and then you use it to determine a probability distribution as follows that depends on the weights of the model, which I've labeled here lambda. Okay? And then by tracing over the hidden nodes, H, you then produce a probability distribution for what's visible. Your goal is then to say, given a set of data which has a probability distribution associated to it, can you tune the weights to approximate that probability distribution? So what restricted Boltzmann machines do is they learn and replicate probability distributions. Okay? And then once you've got that, you can actually extract a host of useful things. So although this sounds very abstract, Jeff Hinton originally used this for handwriting recognition and was incredibly successful. And it's actually used in facial and handwriting recognition and other things. The nice thing is that you don't ever tell the machine what the number 1 is. It just sees naturally that there is a different set of classes that emerge as peaks in probability distributions. And you can use it to what's be called a generative network, which is actually make it produce, if you like, a platonic number 1 by saying where are the peaks in the probability, and it will draw a 1 for you and a 2, even if that 1 and 2 is something it's never seen, just a sample of 1,000 ones. Okay. Now, so what do we do in order to change those weights to match our probability distribution? We need to have some notion of distance in a probability distribution space, okay? And then minimize that distance in some sense. So given a data set, there is something called the Kullback-Leibler divergence, which is defined as follows, where P of t is the true probability distribution that you're trying to model, and that will be given by data, and then P of lambda are the weights in our model, and then this is what's called the divergence, this thing. Okay. Now, actually evaluating this is quite difficult and involved, and we need something called Gibbs sampling and Monte Carlos to do it. And I'm going to mention, actually, we should not just treat that as something to be forgotten, but it's something that's crucial to what the machine is doing. Okay. But this you should think of as really providing us the distance in a distribution space. What Mehta and Schwab showed is that varying the parameters in that Hamiltonian has been related to the renormalization group, and in particular, under a very particular regularization scheme invented by Kadanoff. Okay, so that's, at this stage, a theorem. Now, what will be useful for us is if you are sufficiently near in your model to the true probability distribution, you can expand to quadratic order and then come up with something which is called the Fisher metric, which is essentially defined from the divergence like this. Okay? Now, the Fisher metric is used by information theorists because it has all sorts of nice properties, something called sufficient statistics, which Fisher studied. So this has nice statistical properties as a metric, because you can think of all sorts of metrics you can put on information space between probability distributions. This one has particularly good properties. Okay, and we're going to use this later. A quick remark, which is intriguing in some sense. For a Gaussian probability distribution, you could imagine having that, and then you say, I expect to have a Gaussian model of my data, and I just need to know what the parameters are. So I'm not doing any neural networks, I just want to do model fitting. The Fisher information metric for Gaussian probabilities is the Poincare patch for ADS, which is quite curious. And the width of the Gaussian is the going deep into the bulk. So that's also a little curious thing. So that's the basics of neural nets, Boltzmann machines, and what people do, and information metrics. And I'm now going to turn just for 5 minutes and discuss statistical inferences. Are there any questions about neural networks before I go on to the next bit? You're all happy with Boltzmann machines now? Go on.
Remind me of on the previous slide what the dimension of that ADS space is. How does it depend?
So in the Gaussian distribution, we have d plus 1 parameters. So if I've got a Gaussian in, well, let me just even do one spatial dimension. Then the x naught would be where the peak of the Gaussian is, and the z will be the width of the Gaussian. And then after that, the Gaussian model has no other data that you need to specify other than its width and where the peak of the Gaussian is. So the dimension of the space here is given by is just given by the number of parameters in the Gaussian that you have. So you could have a multidimensional Gaussian will have obviously more centers and then just still one width.
Okay. So I was trying to see how this connects to the neural network, maybe with n nodes.
It does not at this point at all.
Oh, okay, I see. All right.
Okay. So the idea of statistical inference is that you have some model, so that you know that, for example, it was Gaussian or Poisson distribution or whatever it may be. You have some model, and then what you want to do is, given a data set V, to say what is the probability that the model of that model being true, given that data. Okay, and that's you need to do some work, because what you can always work out is, given a model, what's the probability of getting the data, which is what you have here. Oh dear, 1 minute. Yeah, which is what you have there. And then these are what are called the prior probability distributions associated with the model and the data on its own. And then statisticians discuss the whole thing about priors a great deal. But this relation is what allows you to compare different models and then try and sort of eliminate the prior as you compare different things. Okay. And then things like W here is a measure on parameter space of the model. And so this is the whole point of introducing the Fisher metric, is that measure on parameter space is related basically to square root det G of the Fisher metric in what will happen. So the Fisher metric gives you a very natural measure on the space of parameters in your model. Okay. Now, what you then do is you play just some games. You write that probability for the posterior probability for your data, implying your model as follows, where you've just basically taken out some n, take some logs, and so on. And then for large enough n where your data approximates the true probability distribution, then you can show it's equal to this, where you then identify this term as being the KL divergence that I introduced earlier, plus some extra piece. Okay? So we start off, this is just basically Bayes' theorem, messing around with some exponentials and logs, pulling out n where n is the number of data points. This is our Fisher measure, and then we rewrite this in terms of the KL divergence and some extra piece. Okay? Now when you look at that, you're then naturally meant to say this is a statistical mechanics partition function, where the Hamiltonian, which depends on the data, is really given by the divergence of the model compared to in other words, the difference between the data and the model. There's some natural entropy of the data set itself, and then you're integrating over all the parameters in the model to give yourself the posterior probability, which looks like the partition function. Okay. Now, what's sort of happening here in terms of these two things is that what you're trying to do in your model, yes, you want to minimize your energy, but if the data that you've got has got such a high entropy anyway, then you could easily overfit. So what's happening is you're saying you've really got a sort of free energy in this thing, which is really what you want to minimize when you match the model. And again, n, which is the number of data points, is actually related to 1 over kt. And then once you've got something like this, you can then play lots of games in terms of Gaussian partition functions, and then actually come up with some analytic results in statistical inference, and people have done those games. Okay, now, next step. How do you actually calculate these things given a real situation? Okay, so to actually evaluate that partition function, given large data sets and the sort of things one has, then you need to use some further techniques. So there's all sorts of things. So the main approach that's used is something called Markov chain Monte Carlo methods. And this uses the Metropolis-Hastings algorithm, which I'll explain. So to do this is the following. So this was invented back in the 1950s by Stanislaw Ulem. when he was faced with the problem of, he was in hospital in Los Alamos with a broken leg and was playing the card game Patience, if you know what that is. It's where you have some sort of solitaire game of cards, and then some configurations can't be solved and some can. And then he wanted to work out what the likelihood is of any particular card configuration being solvable. The problem is 52 factorial is too much to calculate with. So he came up with the idea that what you do is sample the space rather than analytically examine the space. So this is what you do. You come up with a sample, you start out randomly and say, let's look at that configuration. You then have in order to define the process, you need an energy function. And then you say, right, let's move randomly and then only accept that as the next sample point with a probability according to the Boltzmann weight as determined by that energy function. Otherwise, you stay where you are. And then you roll the dice again, go a new random way, and then ask yourself, do I move according to the Boltzmann weight? Okay? So this is, if you like, a standard way in which a particle in some thermal state would sample a space. And that was very much what inspired physicists who came up with this. Okay? So already, to define the Monte Carlo method, which is used to evaluate these integrals, one already uses what's called the sampling Hamiltonian to define the acceptance function, which is how you sample the space. Okay? So it had very important properties because what it allowed you to do by having this stochastic approach is that you didn't get trapped in local minima. It had difficulties which convergence and computational speed were not very good. And then it had curious things, which is that consecutive sampling points were correlated, which may be not what you want, but that it had useful properties because of that. So now the natural choice is to use the Hamiltonian that we've already used in our statistical inference model to be actually what's called the acceptance function in the Monte Carlo. Okay? And then, if we look at this infinitesimal variation, then I expand out my KL divergence, and then what we get is a sigma model for a point particle where the target space is given by the Fisher information metric. Okay? Right? So we've now created a sigma model where the Fisher information metric is the metric of the target space, and then y's are basically our world line of consecutive sampling points. Okay? And then the sampling method of this Monte Carlo just exactly leads to a weighted sum over world lines given by this thing, which is basically this partition function is then just the continuum limit of the Markov chain Monte Carlo Hastings metropolis. Okay? So this was shown by VJ, and there's references therein, and people have studied this. Okay. Are we happy? Good. Right. Now, that's what you do with one particle sampling, but you want to then quickly estimate the space quickly and get a picture of the landscape of this information space. So computer scientists came up with a whole bunch of ideas. This is ensemble samplers, where you send several points at the same time. So if you like, you have a gas of particles sampling the space. And then this produces a sigma model, and then this produces a sigma model for n particles, or d particles. But then you could try and do something a little bit different to change the performance, which is just as consecutive time-separated samples are correlated, you could say, actually, I could have a correlation between two or more different samples as I'm taking this space. And you can ask yourself whether that does you any good or not, but you can do it. When you do that, you then obtain a sigma model like this in the continuum limit, where this is now a brane of d dimensions, n dimensions. Now, in fact, it's you go a little bit more general because you're doing this sampling discretely, and then what you've got to be very careful of in order to write this in order to write this is restrict yourself in how the things are correlated so that there's a continuum limit that you can write like this. Not every arbitrary set of correlations will have a continuum limit that you can interpret in terms of a world volume of a brane. But you can write out the ones that do, and that's encoded in something called the adjacency matrix, which I've not written down. But you can think of going from this to a discrete version, and then that discrete version will then tell you how different points are correlated. Okay. Now, for those of you who would like to look into this more, this has actually been implemented. This is called the suburban algorithm because it's a distributed metropolis algorithm. Metropolis was a man, but there you go, people are funny. And this code is available for people to check, and it was done on all sorts of things like multi-Gaussians and Poisson models and so on and so forth. And what they found is that actually there was one dimension which did better for the brane than just the usual random ensemble point sampling. Who wants to take a guess what that dimension was? So it was, of course, the string. So if you choose d equals to 2 and have a two-dimensional world sheet doing the sampling, you get better performance than any other thing. And one of the reasons for that is that it creates a more stable inference model, which is related to the beta function, essentially, as we change the Fisher information metric, as we change the scale of the sampler. Okay? So it's rather remarkable, but all of the things that we know about conformal field theory and stability under perturbations is then useful for when you're doing this sampling. Traditional sampling algorithms are very unstable, and that was one of the problems. Okay, now, how am I doing for time? Oh, good, we'll finish early. So, what we want to do now is put these things all together. So we've got that we have a Boltzmann machine, which will provide us potentially with a probability distribution, a probability model, and that would be given by these weights, which are the parameters then of a statistical inference model. We've got the fact that we know now how to sample within a probability distribution model using these Monte Carlo methods. And so now what we want to do is imagine that we take these weights in the restricted Boltzmann machine, sufficiently restricted so they could be related to metric components in a continuum limit. And then the Bayesian inference model, which sums over all the parameters in the model, will then give us a path integral summing over restricted weights that you could then interpret as a sum over metric components. Okay? And then there's a manifest cutoff, which is given by the fact that we have a discrete sample size. Okay? So you saw before in the partition function that 1 over n was effectively giving us the equivalent thing of h bar. Okay? So then what happens is the Fisher information metric, which is the metric on the space of metrics associated with the Boltzmann weights, is effectively like the DeWitt metric in quantum gravity, in the sense that it's a metric over the space of metrics. And then statements such as the asymptotic ADS in the information metric would then be that the probability distribution should be Gaussian in some limit, and then you'd have a free partition function at that point. But you could go away from it. You don't have to have that. That's just an example of relating how if we have an ADS space in the information metric, what that means for the probability distribution that we're modeling. And then you can decide to use quantum gravity techniques for the restricted Boltzmann machine. So here, I perhaps didn't say what the restricted bit was of the restricted Boltzmann machine. That was the fact we had layer on layer, and we had no communication between layer 1 and layer 5, say. In the brain, our brain, not the membrane, we are not restricted in that sense, and then you can drop that condition, and then of course that allows a far freer notion of quantum gravity in the sense that that you can have a lot more going on. The details of what Boltzmann machine configurations you allow that have a manifold interpretation are not yet understood. So this is very much work in progress, that it's like having a matrix model. Not everything will have a nice continuum limit interpretation, but that's one of the goals, to understand that. Okay. So then you can, after that, you can go to strings and use this suburban sampler, and then that will be strings living in a target space given by the Fisher information metric with the world sheet given by the distributed sampler. Okay. So then you can do string theory there. And one of the things that was introduced by these people a while ago was the fact that you should allow the adjacency matrix to allow the strings to split and rejoin. And of course, you would have a parameter, which in neural network terms will be what's called a hyperparameter, which you from the outside set and tune to allow splitting and joining of your samplers. Now, of course, one of the things which neural network people do is that when they have all of this machine learning, they sit and twiddle the hyperparameters by hand in order to get good results. So are you twiddling your hyperparameters when you do it all the time? So then what we've got to do as an M-theorist is that we do not like hyperparameters. Hyperparameters are dimensionless constants in the model that just get fixed from the outside. So what you should then do is take the adjacency matrix, which gives splitting of things, and then turn that into a parameter in the model, which will then grow you a dimension in the Fisher information metric. So this is the sense in which one does M-theory in neural network learning. You take a hyperparameter, which is a thing that you put in, and then you turn that into a parameter of the model, and then use that as one of the things that you then sum over and gets dynamically determined. Okay. Right. So, some questions and fun and games for you all. Once you've decided that we've got these neural networks and we've got this partition function-like approach that comes from doing this sampling, you can ask yourself, can the information space be compact? Do we have isometries? Can we do T-duality in information space? Can we have a duality manifest formalism in information space? As I say, the string tension is like root n, so that gives us a minimum distance in information space. That's just fine. This is what I've just discussed about GS being something that we can now add and doing information there. And then hopefully this will give us all sorts of things that we can learn. Now, what I've not done when I discussed this sampling is what the boundary conditions were for the samplers. So the natural thing is that they're Neumann, but you could try and work out if a Dirichlet had a natural thing and whether vector fields make sense in terms of this field theory. So as it's set up now, you have a scalar sigma model appears naturally. When we've got the weight of the Boltzmann machine, that gives us naturally a tensor model. But at the moment, it's unclear where you get vector fields from this perspective. So that's a puzzle also. Is there a way to get a vector field theory or a gauge theory from this? This is one for, I don't know, something you discuss in the privacy of your room at home. Could you turn this around and think of our universe as an information space and physics as a sampler to determine the Bayesian inference model? If the equations are the same, then you could. And then you then are led to the thing of, do these information theoretic views of gravity that have recently become popular, such as Renyi entropies and submanifolds and whole approaches to understanding gravity and associated to quantum information, does this help you? Because what you've got is an exact realization of how information is being processed and why we have something like a partition function appearing at all in the system. So I promised I would finish early, and I think I have. Thank you very much.
Questions?
Say something more about how renormalization fits into the story.
Yeah, okay. So if I go back to here, what this energy functional is like is really like the Ising model, where I have nearest neighbor interactions and then the weights are like the couplings. And then what you've got is an energy functional here, and then what you can ask yourself is the divergence that you're trying to minimize essentially looks like a free energy. I think that was in a previous slide. So you say, can I change the weights and rescale them to minimize that free energy? Okay. And that was what Kadanoff did in 1970-something. It's known as Kadanoff renormalization, where it's a renormalization scheme, which he did for the Ising model, where you say, this is a free energy, flow the couplings in order to minimize that as you change scale. So you're changing the scale in the theory, but you do so and regularize it so that the free energy stays minimized as you change scale. So the renormalization is then the change in these couplings while preserving this free energy is defined through this way. Yeah.
Where is in this picture, where are the nonlinear threshold functions that are so crucial in the neural network? I don't see them.
So indeed. Yeah. So all of those nodes have got have got this sigmoid type thing in their activation functions. So they're either on or off in that sense. But so what's happening is you take, say, for example, from the visible layer, or I don't know, take from here, let's go this way for now. You take this and add this and add this and add this, then there's an activation function here which tells you whether it goes into here. Okay, so that's the nonlinearity involved.
Right, but where's this in the picture where you start talking about Hamiltonians and renormalization?
That you don't see. That you don't see. You only see it in the sense that when I evaluate. Okay, you see it in the following sense. When I evaluate what the visible weights are, where are we? Here. Trace over h, do e to the minus h here. I'm summing the deep nodes on, and then whether the visual sites come on is given by that activation function. So I've got the energy thing, which then says how each node flows into the other one, and then whether that node comes on is determined by the activation function. Okay.
But this renormalization group also enter in this. In the case of the Gaussian, the renormalization group parameter is just the width of the Gaussian, is it? Because this is just the Bala-Subramanian interpretation of a renormalization group.
So this is right. So there's another question. I'm not sure what's really happening here, or whether it's just cute, right? So what's happening is, this is where you just have a Gaussian model, so it's something very simple, and it's just saying the Fisher information metric has got this ADS. Now at this point, there's no renormalization going on, but it's so tempting to see that ADS, and that is the scale, and indeed it is the width of the Gaussian. So in that very pure sense of as I scale the width of the Gaussian, I flow into the infrared. Yeah, of course. This is what this is what basically stimulated that. Now, but what you don't see in that discussion is any notion of a field theory being renormalized. What you've got is a fixed statistical model And then you're just changing the scale of the parameters in it, and there's some notion of a metric space. So it's a bit like, I mean, how I view this is that when you've got a fixed model like a Gaussian model, and you've got this sort of thing, it's like doing a field theory on a curved background, but you're not allowed to change the background. When we do the neural network, what we're doing is allowing the background to change itself. So in that sense, it's more like renormalization because you're allowing the couplings to change. Yeah.
So I think you used some intuition or analogy with M theory where you reduce the parameters to 1. Can you say a little more about that?
Yeah. So that was just the observation that whenever one does these neural networks, one has a set of hyperparameters, they're called. And for example, yeah, I should have brought in a. So for example, when we discretize this, because this is a continuum thing, in real implementation, this gets discretized. And then H is like the metric on the world sheet. That becomes what's called an adjacency matrix, which says what discrete points are nearby each other. And then you allow strings to split and join because you allow the adjacency matrix to evolve. So you're allowing the things to go away from each other. So that's a hyperparameter that you would control. And these guys have written code where they just put that parameter in by hand. So now there's a lot of discussion in the neural network community that we don't want to by hand tune hyperparameters. You want the model itself to pick out the value of hyperparameters to be part of the model. And that's what I'm saying is what is like the M theory idea, that what you're doing is instead of having a free parameter like GS, you end up growing a dimension in the target space, because the target space is the parameters in the model, and then have the dynamics, because it will then just become part of the Fisher information metric with an extra dimension, and then have it picked out. So, yeah.
So the Fisher information metric, is it just one form, or are there variants which could sort of be the metric for a positively closed space instead of ADS?
Oh yeah, no, it's hugely, I mean, ADS was just this very special case where we had a Gaussian model. The Fisher information metric is as rich as you like. What I've not discussed is the full manifold structure, because the Fisher information metric, strictly speaking, is only true locally. But the global structure of information space is an open question in these models, and that's one of the big things. And that's why it's interesting to think of quantum gravity and say, well, when you're summing over all of these things, what are you summing over? Good.
Can you say again why Dirichlet conditions are less natural in this?
Okay, because what you're trying to do always in this thing is sample the space, okay? So that was the initial Monte Carlo approach. Dot, 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 thermal move around, get some idea of what the space is. When you're Dirichlet, you seem to be doing exactly the opposite, that I fixed some points and I don't allow myself to sample a whole bunch of those sample things are not moving from there. So I'm insisting, keep on sampling there at the end point of my ensemble of samplers and don't move. That's not natural from anyone would do in Monte Carlo. But in doing this sort of approach, you're left to those sort of questions. So there might well be an answer, and I'll probably find there's a computer science paper somewhere where they've done it for a reason. But there you go.
Okay, if there's no more question, let's thank David.